All right, so in this video, we're gonna take a look at a process where we take a set. So let's say I had a set S, and it's made up of the vectors 1, 0, 0, 1. Oops. 1, 0, 0, 1, 0, 1, 0, 2, 2, 1, 0, 4. 1, 0, 1, 4, 0, 0, 1, 3. And lastly, 1, 2, 1, 8. All right. Now these vectors, they're in R4. Okay, all right. Now there are 6 of them. All right, so there's 6 vectors here. Now, I know that this set is linearly dependent, right? Because previous theorem states that I can have at most 4 linearly independent vectors in R4. Now, again, this is not a guarantee that I will have 4. I just know that at most there's 4. So if there's more than 4 already, automatically I know this set S is linearly dependent. All right. So I can remove from this set at least 2 and still have the same span for S. Now, previously what we've done is we've looked at making a linear combination of one vector from the other vectors in the set, but here that can be tedious when there is possible where there's at least more than 2 that are linearly dependent on the other parts of the vectors. So that's where this theorem comes into place. So I'm going to switch over to our book that's going to describe a process on how to eliminate vectors that are linearly dependent. So this is Theorem BS, or basis of a span. So the theorem says that suppose that S is a set of vectors v1 through vn, column vectors, and we define W to be the span of S. All right, and let A be the matrix whose columns are the vectors from S, and let B be the reduced row echelon form of A, with D being D1 through DR. It's the set of indices for the pivot columns of B. Then I'm going to define T as the column vectors, the original column vectors of those pivots, right? That's what part 1 is telling me. Okay, and what this states is that W is the same as the span of T. So this process is a way to eliminate these redundant vectors. Okay, so let's see this in action. I think it's better just seeing this work so we can get an idea of what the process is and what is going on here. Okay, so we have this set of vectors. So we'll start by creating first a matrix where the columns are made up of these vectors. So that looks like this. 0, 1, 0, 2, 2, 1, 0, 4, 1, 0, 1, 4, 0, 0, 1, 3, and 1, 2, 1, 8. All right, so we set up our matrix where each of these are the columns here. Now I reduce row echelon form. I get this to reduce row echelon form. And we get the following matrix: 1, 0, 2, 0, negative 1, 0. And we get 0, 1, 1, 0, 0, 2, 0, 0, 0, 1, 1, 1, and then lastly a row of zeros. So it looks like we have 3 pivots here. Okay, so what theorem BS states is that, again, these columns, now they're not V1, but they correspond to the V1, V2, and V3. So what theorem BS states is that now I can create this new set, T, made up of, going back to the original matrix, V1, 1, 0, 0, 1, V2, 0, 1, 0, 2, and V3, which is, oh, excuse me, not V3, V4 here. 1, 0, 1, 4. Okay, so I create, again, I don't have to find linear combinations of anything. I just choose the original vectors that corresponds to the pivot columns in my reduced row echelon form. All right, and now what theorem BS tells me two things about this. One, that T is linearly independent. Okay, and two is that the span of T is the same as the span of S, my original set. Okay, so that's how we apply our theorem here. Okay, to find linearly independent sets by getting it in reduced row echelon form, and then from there, just choosing the original vectors that correspond to the pivot columns.